All right, welcome to Lesson 6-2b. It's solving differential equations, but this time we're going to find what's called a particular solution. So just to kind of put this in context of something that you've hopefully seen or are familiar with at this point. So in front of you, you can see this slope field. Now, yesterday's lesson, you were finding general solutions. And remember, what that meant was your answers still had that plus c somewhere in that equation. So in other words, you were finding the general form that every possible solution would take on. And that's why when you look at the slope field, you sort of see this repeating pattern. Because in this case, all of these patterns are the same, they're just differing by a constant being added. So they're all vertical translations of each other. And that's kind of the idea behind a general solution. You're just finding the general form where all of them are differing by, say, a vertical translation. Now, a particular solution, you've already seen this also when you saw a problem where they asked you to draw a specific curve through a given point. So they gave you this point, and then you had to try to draw the curve through that within your slope field, and it would look something like that. Hopefully yours would look better. And then something like that. So that blue curve that I just drew, and that's going through the point -2, 0, that's actually a particular solution. It's one very specific equation or function that would be a solution to the differential equation because it goes through the point -2, 0. So what we're going to be finding today then analytically is we're going to take the same process you just used to solve a differential equation for the general solutions, but now you're also going to be given an initial condition that allows you to find the specific constant that makes it a particular solution. So that's what it is that we're looking at today. But again, the majority of this process is exactly what you just did in the previous lesson. Now we're just going basically one step further with it. Okay, so we're just going to look at a few examples here. So we're going to find the particular solution of the differential equation that satisfies the initial condition or conditions that are given to us. And so for this first one, we're looking at f prime of t equals 4t minus 3t squared. And then right here we have this initial condition. This is saying that our solution has to pass through or include the point 1, -5. So in other words, when t is 1, the output needs to be -5. So sometimes your initial condition could be written this way using function notation. Other times it might be written as an ordered pair. In this case, it would just be 1, -5. So just be sort of open to the idea that your initial condition could be given in one of a couple of different ways. Okay, so to solve this particular solution, first we're actually going to find the general solution. So this is f prime of t. I'm going to go ahead and rewrite this though. This is actually going to be df dt. And it really doesn't matter what letters you use. You can change it to a dy dt if you would like. It doesn't really matter. So, and in fact, let's do that just so it's a little more familiar. So dy dt. So I'm really saying that y is f of t. That's really what I'm saying here. So dy dt equals 4t minus 3t squared. Everything has a t, so I'm going to leave everything on the right side, but I am going to move this dt to the right side. So I get dy equals 4t minus 3t squared dt. And now I can integrate both sides. Now on the left side, when we integrate dy with respect to y, that's just going to be y. Equals, now here we're going to use our reverse power rule, so that's going to be 4t squared over 2 minus 3t cubed over 3 plus c. And then we get, when we simplify, y equals 2t squared minus t cubed plus c. All right, so now that is our general solution. But now we get to use our initial condition. And this is telling me that when t is 1, y has to be -5. So we're going to substitute those values in. So I'm going to put a -5 for the y. And I'm going to put a 1 for the t. And that's going to allow us to solve for c. So I get -5 equals, so 1 squared is 1, and then 1 times 2 is 2, minus 1 cubed, which is 1, plus c. That's going to be 2 minus 1, which is 1, and then I'm just going to subtract that from the other side, and I get negative 6 equals c. So that means, now remember, I substituted into this line here. So that means my particular solution becomes y equals 2t squared minus t cubed minus 6. So that's that c that we originally had, but now we have a particular solution right here. And that means this is a particular solution curve that would pass through the point 1 comma negative 5. All right. All right, let's look at a second example here. So this time we have the differential equation dy dx equals xy with the initial condition of y of 0 equals negative 3. So in other words, we have the initial condition of 0 comma negative 3. So once again, we're going to start by using our separation of variables. I'm going to divide both sides by a y, or multiply by a 1 over y. And of course, I'm going to multiply a dx to the other side, and we get that. And so now we can go ahead and integrate both sides, and we get the natural log of the absolute value of y equals x squared over 2 plus c1. Now, yesterday, and I'm going to just sort of say this now, in the previous lesson, I made a really big deal about making sure you keep track of your constants as they change. And the particular solution is the reason for that. And I'll talk more about it after we get there, but I just wanted to point out right now, I'm going to call this initial constant that I get C1. Okay, so now, remember, in order to get the y by itself, to get the natural log out of there, I'm going to go ahead and make both sides a power of e. So now we're going to have the absolute value of y equals, now e to the c sub 1 is going to be a new constant that I'm now going to just call c. And then times e to the x squared over 2. So this is now our general solution. Again, notice C1, that was the first constant I got. This is now just C. This is a separate constant. Remember, C is actually equal to e to the c sub 1. So these are two different constants. I cannot emphasize that enough. All right, so now we're going to go ahead and use our initial condition. So now I am going to go ahead and rewrite this as just y equals. And remember, the reason that I don't need that is because the c is going to absorb whether that y value should be positive or negative. So this is what I'm going to substitute into now. So now I'm going to use my initial condition of 0 comma negative 3. I'm putting in a negative 3 for my y, putting in a 0 for my x, and then that's going to be negative 3 equals c times e to the 0. E to the 0 is just 1, so we just get that c is negative 3. So that means that my particular solution becomes y equals negative 3 e to the x squared over 2. Now, what I want to point out, notice that I substituted my initial condition into this form of the equation, of the solution. And notice when I substituted into this line, the constant that I was finding was this c right here. Oh, that highlighter is a little too dark. So what I was finding was this c right here. This is a different value, though, from this c right here. And the reason I'm making such a big deal about it is, once you've integrated, so after you've done this step and you've gotten your antiderivatives, you are actually now welcome to substitute your initial condition at any time. So we could have substituted the 0 and the negative 3 right here if we wanted to. What we would need to understand, though, is the constant that we're finding is this constant c sub 1. And so after I find that constant, this is what I would be replacing with that new value. And then I would continue the rest of my process solving for y. Okay, so again, it is important that we keep track of the different constants as they change and morph throughout the problem, because depending on which step you substitute your initial condition into, you are finding a different value of the constant. Okay, they are eventually all going to lead to the same final result, but it depends on which step you're at in terms of finding the constant itself. Okay. All right, we're just going to do one more here. All right, so this last example that we're going to look at here, so we're given f double prime of x equals 3, f prime of 1 equals 4, and f of 2 equals 6. Now, one of these is our actual differential equation. The others are the initial conditions. So hopefully you recognize that this one right here is our differential equation. And you should recognize that because it still says f double prime of x. That's the dead giveaway here. Okay, so this right here is our differential equation. So we actually have two initial conditions this time. Notice that one of them is for f prime and the other one is for just f. Because remember, to find our particular solution, this is actually the particular solution of f. So we are looking for f of x. Okay, so to start with, well, we have f double prime of x, which remember is really the second derivative of y with respect to x both times. And so now, when I integrate, oops, a little too soon to integrate here, hang on. So when we do that, we're now going to have the second derivative with respect to y of 3 dx with respect to. And so now, when we integrate, remember that this is now going to be dy dx, because the antiderivative of the second derivative is the first derivative. And then this is going to just be 3x plus some constant c. Okay. Now, this notation is probably more confusing for you, so I would actually discourage that. And what I would actually suggest you do instead, so I know you probably just wrote that, here's what I would actually suggest you do instead. Remember I said, as long as we do the same thing to both sides, it's an equation, so we're fine to do that. I'm going to integrate both sides with respect to x. So it's a slightly different approach to that initial step of integrating here. And so now, the antiderivative of f double prime probably makes more sense to you that this is just f prime equals, and here we get 3x plus that constant. So now we can take this initial condition that we know, and remember, we know that when x is 1, f prime is 4. So when x is 1, f prime is 4. So 3 times 1 is 3, subtract that from both sides, and we get that c equals 1. So now we get f prime of x equals 3x plus 1. But remember, we're not done until we actually find f of x, not f prime. So now we're going to do the same process again. So I've got f prime of x equals 3x plus 1, and now I'm going to integrate both sides with respect to x. And so now your antiderivative of f prime is just f. And then antiderivative of 3x plus 1, we get 3x squared over 2 plus x plus, now I don't want to just say c, because remember, we already referred to c in the same problem. And if I put the same c here, I'm now implying it's the same constant. So you can either call it c sub 1, you can use d instead. So it doesn't matter, but just don't call it the same. So I'll just call it c sub 1. All right, so now we can use our other initial condition. That tells us that when x is 2, f is 6. So I know that f is going to be 6 when we replace the x, or the x's, with a 2. And now let's go ahead and simplify that. So I've got 6 equals, now 2 squared is 4, 3 halves times 4 will be 6, plus 2, plus c sub 1. 6 plus 2 is going to be 8. Subtract that from the other side, and we're going to get negative 2 equals c sub 1. And finally, we get that f of x equals 3/2 x squared plus x minus 2. And that's our particular solution. Now, a problem like this, where a problem like this kind of comes in handy as an application is if you think back to when I first introduced higher order derivatives. One of the first things that I talked about was the application of position, velocity, and acceleration. So for those of you who are in physics, or even if you've seen this as an application, you may recall that there's a general position formula that looks like this. Oops. Plus initial velocity times t plus initial position. So you might recognize that this is position in meters with respect to time measured in seconds. And that formula is one that you can sort of just use. Again, v sub 0, that's your initial velocity. S sub 0 is your initial height or initial position. And so where this actually comes from is a result of what we just saw on that last example. Now, some of you may or may not know this, but acceleration due to gravity is negative 9.8 meters per second squared. But remember, a of t is really s double prime of t. So if we then know that our initial velocity, so the velocity at time 0, is some number v sub 0, and we know that the initial position, or in other words, s of 0, is some value s sub 0. So now, if I wanted to find velocity, I'm just going to integrate with respect to t. And so now the antiderivative of a of t, remember, gives me v of t, its velocity. And then this is now going to be negative 9.8 t plus some constant c. But now remember, we know that when the velocity, or sorry, when the time is 0, the initial velocity is v sub 0. So that's why we get that the constant is just v sub 0. And so our velocity function now becomes negative 9.8 t plus v sub 0. And so now, to find our position, we're going to integrate one more time. But this time, we're integrating velocity. But again, still with respect to t. So antiderivative of velocity with respect to t is just position. Now, negative 9.8 t squared divided by 2 plus v sub 0 times t plus my new constant c sub 1. So now that's going to give me s of t equals negative 4.9 t squared plus v sub 0 of t plus that new constant. And then now, if I put in a 0 for t, hopefully you would see that constant 1 would just equal s sub 0. And so finally, you get this position formula. And that's where that comes from. Okay, so that's a real common application of finding a particular solution from a second derivative that's a constant. It's something along these lines. All right, so this is finding a particular solution. Again, it's very much exactly what you just did in finding a general solution, but now you're finding the value for the constant. All right, good luck.